So hi, I'm Alex,
Porter.
and we're gonna be talking about first error correcting codes. And yeah, so let's get into it. So for an outline, we're gonna start with cyclic codes. We're gonna dive into a special example of cyclic codes, which are fire codes, which work well with first error correction. Then we're going to go over unary codes, and then we'll save the last topic. It'll be a nice surprise at the end. And it'll really tie everything together. So, for first off, cyclic codes. So, even before we talk about cyclic codes work well with burst errors. Now, what's a burst error? It's some error that occurs in some like short span. So if I have some error vector, I can see that the error itself only takes up 5 spots. So we sort of have a burst error description that says we have a burst error that has 5 bits, and it starts at the second index. So we describe it using the error itself, or the parent of the error, then L as the starting index. So 11001 describes this error right here. And then burst errors are common in the real world. Packets can get dropped during transmission, you can scratch a CD. Errors typically happen all at once, and they're not randomly distributed. So this is why burst errors are a thing. This is why we like to group them and have a nice, concise description. So now we'll talk about cyclic codes. So cyclic codes are invariant under rotation. So what this means is if I have some code word, I can rotate it. So take one bit off the end and tack it onto the other end. So here I take the 1 off the right end, put it to on the left end, and so on and so on. They're all the same. And now that we have cyclic codes and we're willing to rotate our code words and do all that, our error descriptions are no longer unique. So now the error we had before, we have the original description, which has 5 bits and starts at index 2. Alternatively, we could start at index 3. And then we have 1, 0, 0, 1, jumping to the other end, 0, 1. And similarly, we have 1, 0, 1, 1 as another description if we start at index 6. So now we can get error descriptions of varying lengths. We can also rotate the error itself because we can rotate code words. So now we can rotate the errors as well. And then the error descriptions can change further. So yeah, that's a fun thing you can do. So now we have these errors that can rotate, and these cyclic code words. Now we're going to talk about linear cyclic code word things. This is slightly review from a previous meeting, but we use what's called the linear part of the linear cyclic code word isn't too important to understand. It's just an extra property we get by using generator polynomial. Again, the linear part isn't really necessary to understand this, but we get it for free. So we're going to take the coefficients of some polynomial that has degree, in this case 4, some degree, and we take those coefficients, and it's either a 0 or 1, and if it's a 1, well then we have a 1 in the corresponding spot of our code. If it's a 0, then we have a 0 in the corresponding spot. So we can encode both code words and errors as a polynomial. And we can choose an arbitrary polynomial as a generator polynomial. So we're using polynomials as a generator, which we'll get into, and as both code words and errors. Multiplication by x is rotation. So x times the example above essentially shifts everything over to the right by 1. And then we have a new x to the 5th term because we want to keep everything as 5 bits. Well, mod it to get it down to 0x to 0, bring it over to the left end, and then we've rotated our code over by 1. hence it's cyclic, because it rotates. So, essentially, the strategy that we're going to be employing, we have some message W, which we're going to encode by multiplying by our generator polynomial. So W's a polynomial, g of x, our generator, is a polynomial. So we get some polynomial. And then we transmit that polynomial, but there's some error. This extra e of the x term. What we can do, if we divide by g of x, we'd have that error term as remainder. So instead of dividing and taking the remainder, we just mod by g of x, and we get e as our error. So yeah, e of x is obtained as our remainder. So for an example for this, we're going to take a nice binary, or all binary strings that go up to a length of length 2, and we're going to encode all of these. And I arbitrarily picked 1 plus x squared as a generator polynomial. So our first step for encoding these, we write them all out, and then we convert them to polynomials. So the leftmost bit that corresponds to the coefficient of our x to the 0 term, the next bit corresponds to our coefficient of the x to the first term. So when we do this, we get our polynomials, and then we can multiply them by our generator function to encode them. Once all that math is worked out, and once the clicker works,
you're pointing to the laptop.
Yeah, need to remember that. Then we get the following polynomials, which we then retranslate back to actual binary, same strategy as before, and we get these 4 code words. So one thing to maybe notice is that the first and third digits are always the same, they have the same variety, and the same goes for the second and fourth digits. So yeah, there's a nice pattern to these 4 code words. And say I received something like 1 or 0, 1, 0, 0, and I know what my 4 possible code words are. If I receive 0, 1, 0, 0, I know that some error occurred. So then, same example as before, we're using the same generator, the code words we just got, and now I received 1, 1, 1, 0, and want to figure out what the actual message that was originally sent was. So, assuming there's only one error, which let's hope there's only one error, we can first encode 1, 1, 1, 0 as a polynomial, divide by g of x, our generator, which is 1 plus x squared, which is 1 plus x over 1 plus x squared. So we have x as a remainder. X corresponds to 0, 1, 1, 0. Yeah, 0, 1, 1, 0. And from that, we can get our original message by subtracting the error from our message that we get. So yeah, that's any questions about using generator polynomials and this encoding decoding scheme? All right. So
Okay, so cosets is that how you say it? It's the cosets? Okay, I always thought it was like maybe cosets. So it's just the set of all the errors after when you get the remainder when dividing by the generator. All errors that differ by some valid code word. Which is usually not super interesting for cyclic codes, but it has some good properties that we can exploit for burst error correcting codes, specifically for fire codes later on. So for example, we have the error from the last line, the 0, 1, 0, 0. And these are all the valid code words. If we add each of these to this, so 1, 0, 1, 0 plus 0, 1, 0, 0 gives us this. So each this, and this are all in the same coset together. There we go. So then this is kind of what I was talking about, exploiting the cosets, for fire codes, or for any burst error correcting code in general. If we have that every, burst error, or if distinct burst errors are in distinct cosets, then it's a burst correcting error. That I'm not gonna prove this lemma, it's not super hard to prove, but it's also not very interesting proof, so I'm just leaving it out. Okay. So this is just kind of like to build a little bit of intuition. For cosets and like what that means for distinct errors being in distinct cosets means that can be, we can correct the birth errors. If we remember this code from before with the, just like triple the bits, and then do majority voting. So if it differs by 1, 0, so would that be this one, this one, this one, it would come here. So these 3 nodes on this graph, are all corrected to the 0, 0, 0. This isn't a cyclic code, and it's not burst error correcting, so this is like kind of a bad example, but just the idea is that this set like all corrects to here. It's kind of a similar idea for the distinct errors being in different cosets. It's sort of like, then like they can all be corrected back to the original message. Kind of a bad example, but this is just a good like visual hand wavy idea. Okay, so fire codes, it's a type of binary burst error correcting code. So it's just 0 and 1 still. Invented by Philip Fire in 1959, so it's been around for a while. I don't think he called it fire codes, but that's what they're called. They're named after him. So I'm just gonna start by like building it up. Like what is a fire code? And then I'm gonna go through how to prove it. That it is the different errors must be in different cosets, so it must be a burst correcting code. So we start with some prime irreducible polynomial, which just means that it can't be factored into smaller polynomials with whole number values, which is kind of the same as like prime integers, which is like, all of this is going to seem arbitrary now until it becomes important later in the proof, so just bear with me. Then we choose some row to be the smallest integer, so that 1 plus x to the row is divisible by our irreducible polynomial. This row is the period of any polynomial, not just cyclic codes, and we're using that here. And then we take some L to be not divisible by p and smaller than m, and m is the degree of the irreducible polynomial. And then we finally, if we put it all together, plug in L, 2L minus 1, 1 plus x to that, times p is the fire code. And then kind of still random, so we're going to do an example of some arbitrary irreducible polynomial, prime polynomial. This could be, there's other things, but this can't be factored into smaller polynomials. And m here is 3. So then we find some row. This is a property of cyclic codes, which we don't really need to go over, but we can find a period using this formula. So we find that row is 7. So then we can choose any L less than m, which is 3. So we just choose 3. It could be smaller than that, and if it's smaller, then we just end up with a smaller burst error correcting fire code. And 3 is 2L minus 1 is not divisible by p. Then we get 5. It's not divisible by 7, so we're good. So then plugging everything in and expanding it out, we get this generator polynomial for the fire code. So this is a fire code and 10 correct errors of length 3 or less. So here's the proof that I was talking about. Fire codes can correct burst errors of length less than 3. This is using the lemma from before that different errors have to be in different cosets, and then it's a burst error correcting code. and we're gonna prove it by contradiction, we're gonna say that we have two different errors, and what if they're in the same coset? And then we're gonna show that it's not, those actually aren't distinct errors. If they're in the same coset, they must be the same error. And then we're just using this lemma here that the factors of P, or the factors of G, these two. That's how we built our generator polynomial, that those are relatively prime. It's not super hard to prove, but I'm leaving that out just to save time. So like I was saying, we take two different burst errors, that are like possible for us to correct with this code, so the lengths have to be less than our L. So then we have these two errors here, and kind of this goes back to the burst error description, where the first bit is an error bit. We know that the first bit of our burst is wrong, and we know that the last bit is wrong. So each of these A1, A2, B1, B2, those could be 0 or 1. It doesn't have to be an error, but the first bit and the last bit are 1, which is classified as the burst error. And maybe these are different lengths, maybe they're the same, but they're distinct errors. And because they could be anywhere, we give them a factor of x to the I, so that it kind of shifts over something. And then we without loss of generality, I is less than j, so A starts first. And we limit it to be less than n just for convenience. So then, like I was saying, for contradiction, we're gonna say that they're in the same coset. They're different errors, and they're in the same coset. But then we're gonna eventually see that this must mean that both of these errors are actually the same error, which is a contradiction, and is gonna give us the proof that we want. So then, by the definition of coset, right, this is what it means for them to be in the same coset. So then if we subtract this, x to the j p of x from both sides, then we get, it would be minus on the left side, but we can just say plus because we're working with 0 and 1. So when we subtract by 1, it's the same as adding 1. -1, it equals 1. So we know that adding these together gives us C, which I'm calling V, just some polynomial in the code. And then this is another, seems arbitrary, but it's gonna make sense later. We're just dividing j minus I by 2 to the L minus 1, and then B gives us the remainder. And then we're gonna take that. So we just have some B and some Q to make that true. And that's gonna be important in a second here. And then so we have, as before, this is our new word that's in the code. And so we're gonna add in this just like arbitrary thing. This works because we're multiplying it by 2. So if the coefficient is 0 times 2 is 0. If it's 1 times 2, it's 2, which is 0. So that's just 0, so we can just add that on for free. It seems random, but when we rearrange it, just with algebra, this gives us a useful new arrangement that we can take advantage of with this. If we divide it by G, we know it's a code word, so it has 0 remainder when we divide by G because there's no error. We know then that the second part, this, is divisible by, well, okay, so we have the lemma from before that the two parts are relatively prime. So each side of the plus has to be divisible by each one of these. So we take this side and we can divide it by this 1 plus x to the 2L minus 1, even though there's a q there. It's a little bit not obvious, but you can prove that this will divide this, which means that because they're added together, this has to also be divisible by this, unless it's 0. And this, unless it's 0, it's going to turn out actually is 0, because it's going to turn out that the errors are actually the same. So we're going to create some d to be the quotient after dividing by this, and we're going to see that that has to be 0 for this to make sense. Okay, so this is after we divided, so we have this, right? And we divided it by this and define that to be d, so we can kind of just rearrange it to be this. And then we have delta to be the degree of d. These are all the degrees of each of these parts here. So we know the degree of this is this, and like the degree of a to the x has to be that by our definition of a, because it's a length of L one. Okay, so L minus one, this is just a this is just a fact unrelated to this for now. That L minus one is less than 2L minus one because L1 is restricted by L. So doubling it is strictly less than instead of just less than or equal to. You can just like ignore the ones.
It's that might be dying.
Yeah.
Just do the arrows.
Okay.
Yeah, just click and I'll press the arrow. I'm the clicker.
Okay, so then we have this here to be this, and this guy is the degree of the whole right side. And we know that this, the degree of this has to equal the degree of this, because this is less than the degree of this. So for these two sides to be equal, the degree has to be the same. So if you just look at this one, that alone isn't enough to be the degree. So we know that the other side, this b plus L2 minus 1, has to be the same as the degree on the left to compensate for that side. So then just with algebra rearranging, we get that b is greater than L plus delta, which then gives us these next 2 points, which, okay, kind of random. But on the next slide, okay, so using this first one, we know that in our expansion of this, right, this first line here is A, and this second line is B times x to the B. We know that x to the B has to appear in this. It's not going to get canceled out because this multiplies by the 1 here, so we know there's an x to b here. And it's not going to appear later, so it couldn't cancel out there. And then with this, we know that because b, this power here, is more than the power of these, we know that this term, the x to the b times this 1, is going to be greater than all of the possible terms in b, so there's nothing in a that could cancel out with b. Which then gives us that because b is greater than delta, we know that the quotient from before, the d, doesn't have an x to the b term, because then the degree doesn't make sense. So we know that this whole thing here is not divisible by our d. And like I was saying before, that gives us that it's not divisible, so it must be 0. Okay, so then now that we know that it's 0, now we know that we can right, b becomes 0 because, which means that it's not offset at all, right? The b is the term to which how far b is shifted over, because it's multiplying by x to the b. So if we know that it's 0, we know it's not shifted at all, because we have to have that this 1 and this 1 cancel out, right? For this to be 0, we have to add 1 plus 1 equals 0, because we're still in F2. So we know that b has to be 0 for these ones to cancel out. And then if we have that, that gives us that both of them have to be the same, because then this term here and this term here have to cancel out, and each term in the middle also has to cancel out. So they have to be the same error, which we assumed at the beginning they were different. So that gives us the contradiction that we're looking for. So we know that this group really is true. Right. So if they're different, they're in different cosets. Okay, so from our example from before, this was our generator polynomial for this fire code. Just like putting these variables here so we can look at it again, because I'm going to put some formulas up next. We know this is just another formula that the block length for a given fire code is the least common multiple of 2L minus 1 and b, which that like shows up in the proof. If you like really get into it, you can kind of see why that makes sense. And similarly for k, the original message length is this. You can see this is the block length minus m, which is 3, and then minus 2L plus 1, which is 5. So you're subtracting each of these. Again, you can kind of, it's not super hard to see that, but I didn't want to get really super into the details of that. So then that gives us the message length for this example. So we have the 27 and the 35. So for a block length of 35, we're encoding messages of 27, which if it were a Hamming code, this is like fake math right here. Because a Hamming code is, obviously you can't have bits that are partial bits. And you can't have Hamming code actually doesn't work out to be, you can't have a block length of 35 for the Hamming code. But just in general, the idea here is that it's pretty close to the Hamming rate, which is good. And it also gives us the Hamming code only corrects one single errors, but the fire code can correct burst errors. So this particular one corrects bursts of length 3, but a Hamming code of this size would only be able to correct 1 bit. So even though the density of the message in the encoded full block is less, it still is correcting more errors than a Hamming code because we have the additional restriction that burst errors are only a certain size. So it's actually really good. And then if we draw on the graph here, it's good compared to Hamming codes, but compared to Reed-Solomon codes, which are not strictly binary. The yellow here is the fire code, and these are all the Reed-Solomon codes. These are better. And we're not going to talk about that. Anakin's going to talk about that in a later reading. But yeah, that's fire codes. Any questions? Yeah.
Can they correct errors of length, like when you talk about Greek, error of 2?
Yeah. Yeah. Any error of less than 3. And like for the error, that the first and last are error bits, and any bits in the middle could be an error bit or could not be. So there's as long as there's the location of all the errors that happen is less than your given length 3, you can correct it. So yeah. X to the what? What is it?
Yeah, I guess we probably they go for it. No, I keep going. No, but so L here
Yeah.
would be
This?
right.
Yeah.
Oh yeah.
That's just like a way for in the proof, that's kind of the choice that makes it end up working. I guess that's maybe not a satisfying answer, but yeah, you can get like really more into like the properties of like what makes that happen. But the short answer is that's the number that makes it work when you like reconfigure the terms in our ax plus x to the j times b to the x that we figured out was 0. The configuring of that is useful to have this be 1 plus x to the 2 on 4.
Likely what's happened is when this guy was doing his dissertation, he was going to the analysis, like, I don't know what this is gonna be. He did all the analysis, like, oh, if I choose 2L equals 1. Like, if I choose 2L minus 1, it works. So, like, not satisfying, but it's part of the reality.
And actually I'm pretty sure it be oh no, never mind. I was gonna say it could be -1 or +1 or whatever. But that's actually this could be a minus instead, and then actually ends up working out. I found another proof of that. So yeah.
So we take the minus response. Find the value.
Yeah. Except it's not a random polynomial. It's important that this is an irreducible polynomial, right? A prime polynomial, because then we know that that gives us that they're both relatively prime. So then we know if we go back more, I don't know if we can go back like forever. It gives us that at some point, because they're separate, we know that it has to divide the 1/2 and not the other half. So then yeah.
I didn't quite get that.
Here, let's find that.
Relatively fine.
Yeah, this part. So they're relatively. So which part did you get? That they're relatively prime, or this dividing part?
Oh,
So like, we know like this V is some code word. And there's no error in the code word, so we know that when we divide by our generator G, there's not gonna be any remainder. So just like, this is just like a property in anything with addition, if it's divisible, by, in this case, G, we know that this half is divisible by G and this half is divisible by G.
It's not that, it's because. So V of X is divisible by G. And you know that, V of X must, like, like the second term is divisible by 1 plus X to the 2L minus. So the second term is. And then that first term must
Right.
also be divisible by that. Because if you know, like, the left-hand side is divisible by like the term, and you have the sum of two terms, and one of the terms is divisible by that same thing, then that third term must also be divisible. Because otherwise you reach computation, like, if you subtract.
Like, in a relative term, nothing, like, it's divisible by the entire the one plus X to the L.
You might be divisible by the rest, but the key part
Yeah.
is.
And then we get that they're relatively prime, from the fact that we get the prime irreducible polynomial that we started with at the beginning. And that's part of where the choice of this 1 plus X to the 2L minus 1 comes from, because that choice forces them to be relatively prime. Any other questions?
You go forward with the plan.
Here. Back. With the degrees,
Wait, this slide or the one previous?
I'm thinking about.
are you talking about this one?
No, that.
Okay. All right.
Alright, well. So fire codes are fun and they work well, but we've also spent a lot of this semester talking about codes that aren't linear cyclic codes and don't have all these properties of fire codes. It'd be nice if we could use them again. So now we're gonna go over interleaved codes, which will build off of previous codes that we've worked with. So the whole idea is that codes like, I don't know, a Hamming code operates under the assumption that errors are going to be randomly distributed throughout our message. And normally that's fine in theory until we get to real life. But what we can do is we know that errors are going to likely be spatially correlated. They're all going to be in the same spot because we're talking about burst errors, right? So if we want to bridge the gap between reality and our theoretical errors are randomly distributed that we like, what we can do is split the errors up. So now the errors are in completely different positions, but not only in different positions, they're going to be in different code words. So that's another thing we're going to do with interleaving. We're going to go from talking about single code words at a time to talking about multiple code words at once. And we're going to leverage the fact that not all of the code words are going to have errors. So then we can take the errors in what would have been one code word, spread them out, and then because we have multiple code words taking up like one error at a time, we have multiple things to lift the same amount of weight. Wow, this clicker likes me. So yeah, build off of the idea of some code, Hamming codes, for instance, that's going to work well with random errors. Not anymore. So after we encode the message, but before we send it, we apply some interleave step. Ideally, we'd like to apply some bijective function so we can get back original message after we interleave it. But basically, we take all the bits, we arrange them in some predetermined way, we scramble them up. Then, so we send the message, and a burst error occurs. So one or a few of our code words are have errors in them, but then we descramble the bits, we de-interleave, and we send those errors to different code words, and now we're going to be able to correct those errors. And also, just to be clear, your bijective function should not depend on the code word itself. It only moves like bits from position 1 to position 7. You're moving bits to different positions. You don't care about what those bits are. So when we de-scramble or de-interleave the code word, the bits are going to their original positions, and the errors don't affect that process. So there are multiple types of interleavers. The first one we'll talk about is block interleaver. This is just one way to interleave. So the whole idea is we have some m by n matrix, in this case 3 by 3, that we can write our bits into the matrix. And typically we write them in row major order. And then a simple way, after they're in row major order, well, we can get a different ordering by reading them out in column major order. So if I feed in x to the 0, x to the 1, blah, 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 get x to the 0, x to the 3, x to the 6, x to the 1, x to the 4, x to the 7, and so on and so on. And this is really nice because this is very easy to implement. You can also envision it as writing in row major order, taking the transposes of the matrix, and then reading it out also in row major order. Either works. So then, now that we have this idea, let's take an arbitrary code word, and we're gonna build off of our favorite code. We're gonna repeat each bit 3 times code. And so we have our beautifully encoded message, and right before we send it, we need to interleave it first. So we take our matrix, we write the bits, 3, third code word, fourth code word, then we read them out in column major order. So the bits are colored just to help emphasize where each bit is coming from, but we end up with 0, 0, 1, 0, 0, 0, 1, 0, 0, and 0, 1, 1. Yeah. So now we send our message and we unfortunately get some error. So we have a burst error of length 3. If this was our original code, if we were just using we repeat digits 3 times, what we'd get some word would not be decoded correctly because at least one word's gonna have 2 errors in it. So that's bad. But we interleaved, so we write it back to a matrix in column major order, sort of the opposite of what we did before, and then we read it out in row major order. So now we get 0, 1, 0, 0, 0, 0, 0, 1, 1, and 1, 0, 0. The important thing is these 3 errors that used to be right next to each other are now in 3 entirely different words, or code words. So then, using our digits are repeated 3 times, or bits are repeated 3 times, this is very easy to corrupt. Oh yeah, the original message should have been good. Okay. So for some analysis, let's say we have some burst of length L, some burst error. We know because we write those errors to the matrix in column major order, and then read out the matrix in row major order, going from one row to another, essentially, or each error in the burst, it's 1 row down. So each row is of I'm getting this a bit jumbled, but after interleaving, our actual distance between the errors becomes size of m of our original matrix. So then, because the distance between errors becomes m, we can fit up to m times L errors of our burst length and spread them out to so that each word will only have up to L errors. But once we add an ML plus 1 error, we know at least one word in our output needs to have L plus 1 errors. And more specifically, we can talk about a burster of length ML plus 1, and because there are multiple errors or burst errors that can have that length, just because we have a burst error that's longer than m times L plus one, it doesn't necessarily mean we have L plus one consecutive errors in our outputs. So thus, any code that corrects T errors, can correct M, where M is the height of our matrix, times T burst errors, because, well, now those MT errors get spread out to be T errors, or T number of errors in each code word they end up in. So we can do some analysis of the efficiency of our black interleaver by seeing how many bits we can correct, and compare that to how much space that we end up using. So black interleaver is a matrix that's just m times n space. And efficiency, our error first fails, or our code, my bad, our code can first fail. Not always, but it can fail when we have m times t plus one errors. And if we divide it by space and by n, we get that, or m times n, we get that our efficiency is roughly t over n. And I should also add as a slight caveat, but this is assuming that the columns of our matrix, or we have the number of columns that we have, n, is the same as the length of our code bit. And that's just standard because it's easy to do. It makes the matrix look nice. It's easy to visualize. So that just it is an assumption that we're going to use later again for a different analysis. And it's pre-common. Okay. So block interleaver, that seems pretty good. We spread out errors, but we pretty much need to read the entire message before we can start to interleave or de-interleave it. Well, really in this case, before we can even start to de-interleave it. For sending small messages, this doesn't matter. But if we have a large data stream where we're continuously reading and updating data, this isn't necessarily as good. One possible solution would be to interleave blocks of data at a time. But then, how do we know when the blocks start and end? And we can bunch things up into packets. So there's a lot more depth we can get into, but so yeah, there's a lot of thought about, can we make block interleavers work well with data streams? But it's really not what they're both. Okay, so now we'll go over convolutional interleaving, because convolution is in everything these days. Perfect word to add to whatever topic at hand. So these are also called cross interleavers. I'm really still calling convolution there, or convolution interleaving. So the idea is a bit strange at first. Essentially, we have our message, and then we have multiple queues. In actuality, these are implemented with delay lines and hardware. So we do get hardware support for what I'm about to talk about. But we send, if we start at like 6, 7, 8, and some items have already been sent into the queues, 6 goes into the first queue, and the first queue has length 1, so then 6 will end up in the output. 7 goes to the second queue has length 2, so then 7 has to wait because it wasn't the first there. Instead, 4 got to the queue before 7, so then 4 ends right after 6 in our output. And then we send 8 to the last queue, but the last queue has length 3, so 8 has to wait for 3 more items, or not 3 more, 2 more items to get off the queue. And once 8 joins the queue, 2 hops off the queue, so we get 6 for 2. And then if we were to continue with this, 9 would hop on the first queue, nothing to wait for there. 10 joins the queue, 7's not done to the queue, so on and so on. So we're maintaining multiple queues of different lengths at once. Now, this is a bit annoying to visualize, so there's a much better way. Wow. That was intentional, I swear.
Hello, please. Oh, Lordy. Where did those go? We're still back.
Okay, so yeah, this is the slide I want to be on. Hey, great.
Oh no. It's not screen. Oh, the screen sharing.
It's screen sharing.
Okay. So another way to visualize this, because shoving things in multiple queues, and just waving your hands and saying, oh, this was in the queue before, so it's gonna work out. It's a bit weird to think about. So instead, we can use a similar matrix strategy as before, and write our elements in row major order, and then to interleave, we shift each row down by like its row number -1. So we take the second row, shift it down by 1. We take the second row, shift it down by 2. And then we have a new row major order. Some of the bits are not necessarily going to be defined, which, yeah, for now, we can just pad them with dummy bits and call it a day. But now we have an order of 0, dummy bit, 3, 1, dummy bit, 6, 4, 2, and 6, 4, 2 looks familiar because that was previously on the previous slide of some of the output of this convolution interleader. So yeah, this is another way to get that output. Shift your columns down, read in row major order. So to de-interleave, it's a bit less intuitive, but essentially just switch the order of the queues so that first elements go into the longer queue, and later elements, at least going queue by queue, end up in the shorter queue. It's a bit easier to see with the matrices because we just, instead of shifting the right side down, we shift the left side down. Then we can recover our original message. So again, we're going to do an example. This is the same message as before. So we write it in our row major order, like before, but now we shift everything down. And the bits that we don't care about, I don't care what's in them, so neither should you. We're just going to pad some dummy bits to make the ends work out. So then we get some message that's a bit longer than it has to be. But for the most part, yeah, it's interleaved now. So now we have some error, and some of these error spots we don't care about. But we introduce some error, and we get a new message to decode. So then we take our message to decode, write it in row major order. Once again, then we shift the left side down by 2, shift the middle down by 1, and then we get a new row major order. So we've actually, in this case, gone from 4 to 3 bits flipped because one of them we really didn't care about. But more importantly, the errors are back in 3 different words, so we can yeah, so our 3 repeated bit coding scheme, we can recover the original message. So to analyze the convolution interleaver, the difference between consecutive bits becomes n+1, where n is the length, or n is the number of queues we have, or if we use the matrix analogy, it's also the number of columns we have in our matrix. Once again, we're going to sort of assume that our word length is just the same as the number of columns in this matrix, because yeah, it's nice and very practical. So we can correct up to n+1 times t minus 1 errors. It's a bit more intuitive to think it's n+1 times t. It's actually t minus 1 because if you suddenly have words start shifted in, then you can get errors, more errors than you want in a word if you multiply by t. It's a fun derivation that we don't necessarily have time. And because we'd like to analyze the efficiency, what's left, we need to compute the space. Our first queue takes up 0 space because we just send that item immediately to our output. Our first queue needs to store one item at a time, and we can send the second item immediately to our output, and so on and so on. So we end up with a summation. Use your favorite formula to find you have n times n-1/2 space to implement the queue system. And because of this, the queue system, we no longer have to read the entire message before we start decoding. We can decode as we go, so this works a lot better with data streams. And then for efficiency, we fail at n+1 times t-1 plus 1 errors. That's where we can get our first more than t errors in our word. We divide it by our space, and we get that this is approximately 2t/n. And notice this is about twice as good as block interleavers, which only had an efficiency of t/n. So this is a major improvement. So now, tying everything together.
Yeah, so that's pretty much it. But unary codes is like kind of just like an interesting little caveat. Because we've been working with binary codes, you can have like, so we're using just 0 and 1. But unary codes is if you only choose to use one character. So if we take like a string of zeros, for example, and then get some error, like those red bits are the error bits, then we can correct that error. This is the message we receive, and then we correct it to the original message. And so this is actually really interesting because you can correct an arbitrary number of infinite errors. So it's actually like the best bound you could have on anything. And it seems like kind of dumb, like it's just zeros, but it has actually really interesting applications in like the complex plane, because it's like really good for like, for example, digital communications with your imaginary friend. You can just like send them any message and it doesn't matter, they'll get the message, it'll be corrected. So that's what unary codes are good for. And that's it.